This is 522. It is November 12th. Today we're going to talk about, finish our discussion a little bit about factor analysis, and then make our way into path analysis and structural equation modeling. So I'm in the Mayer book now, and I just wanted to recap a little bit of what we talked about last time. Last time when we were talking about exploratory factor analysis in the Stevens book, we looked at some of the issues and defined a factor model in factor analysis. So remember we said things like the factor that you're inferring is based on manifest variables, okay, or otherwise known as observed variables. So they're the observed variables there. So in this case, if I hypothesize a one factor structure, I say that the factor is being indicated by these three variables over here. And we talked about some of the issues with factor analysis. We said things like the solution is not unique, okay, meaning that there's a couple ways of interpreting that, saying that the solution is not unique. For one thing, we said that if you extract 3, 4, 5 factors, you may get different loadings depending on the solution that you extract. So that's really important to remember. The other idea is that we can rotate the factor solution. Okay, we can rotate the factor solution. So the idea that you can rotate and just as well regenerate the covariance matrix. So if we call this our covariance matrix, the fact that you can rotate the solution and just as well reproduce this leads us to the problem of trying to decide which loadings are the correct loadings, right? So that was one of the big issues last time where we said we had the loading matrix and we were trying to decide what's the correct loading matrix. Does this consist of, just F1? Does it consist of F2, F3? So how many factors should be in that loading matrix? The fact that we can rotate the loading matrix and still produce this meant that the decision would have to be more or less a subjective one on the number of factors. Okay, that was the logic of what we were developing last time. We also talked about the communality idea. Okay, so when you have your observed variables over here, x1, say x2, x3, and then you have your factor solution, say f1 and f2, well, these are going to be loadings over here, and you want to look at how well does that factor solution account for the given observed variables. Okay? And that was expressed in terms of a communality. One minus the communality was the variability that's unexplained. So, when you have high communalities, that's a good thing because that means that your factor structure is doing a good job on that variable. Okay, it means that your factor structure is explaining the given variable pretty well. Now that, of course, sounds a little bit weird because we're not used to talking about variables like that. But remember, it's the factor structure that's giving rise to the observed variables in the factor analysis model. So it makes sense to think about the observed variable here as a function of the factor solution, right? Notice it's the factor that's pointing to the observed variable. So in this particular sense, it's almost like this is a dependent variable and this is an independent variable because this is leading to this type of thing. Now we normally don't think about it that way. We don't think about this observed variable as being the dependent and this being the independent. But in terms of that communality, that's a good way of kind of conceptualizing that because it reminds us that it's this that we're trying to explain, right? We're trying to explain observed variables. We're not trying to explain a factor. We're trying to explain the observed variables. So if you have the verbal, analytical, and quantitative over here as observed variables, you're trying to explain this. Now, one person's high in verbal, high in analytical, high in quantitative. What accounts for this? What explains it? well, maybe you have a factor solution that accounts for it or explains it. So the idea of a rotation, we talked about orthogonal rotations. There's also oblique rotations. When we talk about oblique rotations, then factors are allowed to correlate. So factor 1 could be correlated with factor 2, whereas in orthogonal, they cannot be, so you won't have any correlation. And recognize that when we talk about these things, oblique versus orthogonal rotations and things like that, those are things that are fixed in the procedure that you're running. Okay, now I want to just really emphasize that because that's going to be really important for what we talk about today. When we talk about the orthogonal rotation, okay, when we talk about orthog rotation, these are not allowed to correlate. Okay, the factors are not, by design, they're not allowed to correlate. Now that's a separate issue than whether the factors in nature are correlated. Okay, and let me just repeat that. When we do an orthogonal rotation, we're not allowing these things to correlate. So there's no correlation possible between F1 and F2. That's not the same thing as deciding that there's no correlation in nature. So maybe F1 and F2 are correlated in nature. So let me give you an example. Let me just get a little bit more space. And let me give you this example that we have, say IQ is a factor. It's indicated by however many variables we want, like verbal, like all these things we're talking about up here. So we're just going to draw the factor here. So it's got the arrows coming out, but I'm not going to draw the arrows. I'm just going to say here's a factor. Let's say IQ is related to self-esteem. Okay, so IQ is related to self-esteem right here. When we do a particular factor analysis model, we can set that correlation equal to 0. We can set it equal to 0. We could choose to not model it, or we can choose to model it. So this correlation here is not necessarily reflective of what's going on in nature, because if you do an oblique rotation, for instance, and you're not allowing factors to correlate, then, if you do an orthogonal rotation and you're not allowing factors to correlate, you're assuming the correlation between factors is equal to 0, right? So if you do the orthogonal, you're setting this equal to 0. It's impossible that they correlate in your particular model. If you do an oblique, then you're allowing them to correlate, right? So this is no longer equal to 0, assuming there's some correlation between them, and you're allowing them to correlate. That should bother us a little bit, or it should make us think a little bit, because either one of these cases does not necessarily represent what's going on in reality. Is IQ related to self-esteem? Who knows? But when you set up these rotations and set up your factor model, you're making decisions on what to impose on the model. Okay. So if you're doing that orthogonal rotation, they're not allowed to correlate, even if in nature there is a correlation. That's really, really important. So this is why it's so important to understand that the choice of microscope that you're using is going to represent certain restrictions on what you will see. Okay, so the analogy here again, I mean, it's not the best analogy. Well, it works, even though like Dr. Birx and Dr. Fauci do not have to worry about this that much, not like we do. But the analogy would be using one microscope 1 versus one microscope 2, you're going to see different things, right? So what you see out here, you're trying to see something, is a function of the microscope you're using. It's not like an archaeological dig where the skeleton exists or it doesn't. And no more is that true than in factor analysis. So we have to be aware of all these things, that the way you're setting up your factor model is going to help decide what you see. So imagine you're at a conference and you hear somebody talk about the orthogonal model and they say, I ran an orthogonal factor analysis and I found zero correlation between variables, between factors, right? Imagine somebody said that. I did an orthogonal factor analysis and I found a correlation of zero between factors. That would be an entirely false statement, right? Why would it be an entirely false statement? It would be false because it was set up to have the correlation of zero, right? It was set up that way. The researcher didn't find a correlation of zero. It was operationalized, parameterized to have a correlation of zero. Now, that situation is different than if the researcher said, I did an oblique rotation and I found a correlation of zero, right? In the oblique rotation, they are allowed to correlate. Therefore, you're able to observe the sample correlation. Those two situations are different. Please be sure you're aware of those two distinctions because they're important. Now, we know from just the way variance partitions that that correlation is not going to equal zero. It's going to be something. But the point is that you can choose to model a correlation or you can choose not to. And that's the difference between finding something versus not. And at first glance, that may seem a little bit strange because you figure, how could we have so much freedom in how we set up our model? But that's how modeling works, is you have to choose certain model parameterizations before you're able to observe what you see. So the ending conclusion here, and something that's going to be returning to a little bit when we talk about this stuff, is if you think there's a correlation between your factors, and it seems reasonable that, what was our variables here? What were our variables? IQ correlates with self-esteem. If you think it's reasonable that IQ should correlate with self-esteem, then you might want to model that path, right? Notice that we're starting to use that path analysis structural equation modeling lingo, which is where we're headed. When I say you may choose to model that path, I'm allowing it to be estimated, right? I'm allowing the path from IQ to self-esteem to be modeled. In other words, I'm asking the program, I'm asking the computer or the algorithm, you can go ahead and model that. If I decided a priori, before looking at any data, if I decided that there's no correlation between IQ and SE, or that I wasn't interested in modeling that correlation, I could choose to not model that path. I could fix it to zero. In other words, the fixing here is an assumption, or you can also think of it as a constraint that the path of IQ to SE, the correlation, is equal to zero. Something that we're going to be returning to. Okay, we're going to return to these ideas. The other idea in factor analysis, just to kind of close up that topic before we look at this stuff more, is the idea of estimating factor scores. So you can get factor scores in factor analysis, and Stevens will discuss that a little bit more. Also, Mayer does as well in the previous pages to this. And when you estimate factor scores, okay, when you estimate factor scores, the important thing here is you're estimating them, okay? You're not computing factor scores in the way of computing principal components. You're estimating them. And when you have to estimate factor scores, oftentimes the regression method is the way to go about that. There's different methods, but the regression method is quite popular. As soon as you estimate factor scores, well, we know that since factors are not necessarily determined, okay, they're not uniquely determined, well, we know that the factor scores are not going to be necessarily unique. They're going to suffer from that indeterminacy problem. And Mayer talks about that, and Stevens will talk about that as well. So just realize that if you do get factor scores, it's not the same thing as getting component scores. And it suffers from the same problem of that indeterminacy, which is what's plaguing factor analysis, right? So we have this theme of it's so important to understand what factor analysis can do versus what it cannot do. And it's got that indeterminacy problem that kind of plagues it all over the place. Doesn't mean it's a bad thing to do. It means you really need to recognize what it can produce. That's why if we draw the analogy to the microscope again, the importance of the microscope is paramount in here. It's not just looking at the data. Okay, you're not just applying some kind of a microscope to look to see if there's the virus. The microscope, in a sense, is almost just as important as whether the virus is there, because the microscope is going to sometimes decide whether you see a virus or not, by analogy. So please be aware of that. Okay, so into Mayer here, we're gonna, Mayer talks about a couple of fit statistics. He talks about this in the context of exploratory factor analysis. So we're still technically in EFA here, but we are headed quickly to CFA, which is confirmatory factor analysis. We'll talk about the distinctions between the two. Remember from the outset in Stevens, we said that the job of factor analysis on a technical level, right? Not on a substantive level, but on a technical level is to what? What was the goal? The goal was to take the correlation matrix or covariance matrix and try to reproduce it, right? That was the ultimate goal. I mean, remember, aside from what theories you have and everything like that, this is what the algorithm is trying to do, is trying to reproduce that correlation matrix. So you have a correlation matrix of variables, right? X1, X2, X3, etc. And one way of looking at factor analysis is it's trying to reproduce it. How is it trying to reproduce that? By getting those loadings. Remember those loadings. So that's why you're trying to determine how many factors are in your data. Well, you're going to get these loading matrices. That's just the transpose of it. You're getting the loading matrix, and then you're generating your factor model. Now, in most situations, the EFA, you're deciding on subjective grounds, right? And we've stressed that throughout, like stuff like this. You cannot use fit criteria to decide how many factors you have here, really, right? If we're completely honest about it, no measure of fit, right? No measure of goodness of fit is going to tell you what your factor solution should be. So the first thing to understand is you can't just look at one indicator and say, well, this is my factor solution. No more than you can look at like R squared for one model in regression versus R squared for another model and decide whichever one's bigger, you're going to go with that model, right? You have to input your researcher judgment on this, and no more is that true in factor analysis, especially true in factor analysis. Regression is even a little bit simpler, but in factor analysis, you got to look at subjectively. But nonetheless, there are some goodness of fit indicators that have been proposed that can be used in exploratory frameworks. They're much more common in the CFA and structural equation modeling that we're going to talk about briefly. But let's look at a couple of these indicators right here. The first one is the root mean squared residual, okay, RMSR. Now, because we're trying to reproduce the correlation matrix, so we're reproducing it, the implied correlation matrix, also known as the fitted correlation matrix, right? Why is it fitted? It's fitted based on your model. There's the important part of the model right there. I mean, we have the psi matrix here, but this is the important stuff. So it's the implied fitted correlation matrix, P with the hat on it. So you can see what the objective here is to see, hey, can we generate factor loadings that reproduce this? So what would we like to see? What would we like to see? We'd like to see R and this, P with the hat on it, perfect match, right? We'd like to have that, the perfect match. That would mean, wow, do we have the correct factor solution? No. It doesn't mean we have the correct factor solution. It means we've reproduced the correlation matrix pretty darn well based on our factor solution. Okay, now that distinction that we just made is important. It doesn't mean you found the factor solution. It means you found a factor solution, okay, that regenerates the correlation matrix. That word is really important, not the. So there again, if you're reading a paper or you're attending a conference and someone says, I found the factor solution, and you say you found one factor solution, no more than you found the correct model in regression. You found one that does a pretty nice job on R squared. Same idea here. So the closer these two matrices are to each other, the better the model fit. So if we look here, we see what this root mean squared residual is up to. RJK, so depending on what position that occupies in your matrix, that's a single element in R. That's the thing you're trying to reproduce, right? You're trying to reproduce this. Well, there's the predicted value, if you like, or the fitted value. Okay. Fitted is probably a better word here in terms of the factor analysis. Usually when we talk about predicted, you think about it in terms of regression. So what's the fitted or what's the implied value for that correlation is that single element here. And you can see what it's doing. I mean, the important part here, these are just the variables, but this is the important part here. Right? Observed minus fitted over here. And I mean, that might even look a little bit similar to the idea of a regression, where you're taking an observed minus the predicted value here. And we'd like that to be small, the better the fit. The discrepancy, okay, the discrepancy between these two, we'd like it to be small. And this RMSEA is an example based on these types of what are called discrepancy functions of the maximum likelihood estimation. And there's a whole host of discrepancy functions. This is one type of thing that uses concepts of discrepancy, but there's a whole bunch of other discrepancy functions as well. This is a measure of what's usually called absolute model fit. Okay, so we usually call this a measure of absolute model fit because it's not really comparing anything to like a baseline model. It's just computing those differences between observed versus implied. We get to this model fit over here. This is the Tucker-Lewis index. And this one here is, you can think of it as a comparative fit index. Now, why is it a comparative? Well, it's comparative because it's comparing the model to a worst case model where you have a zero factor model and a best case with our fitted model. So we have a worst case, we have a best case here, and it's looking at that discrepancy over here. And it has a denominator here, but the important part is that it's looking at the discrepancy relative to the worst case and then the best case over here. And the TLI, you'd like that to be a large value. You'd like that to be a large value by the nature of how this works over here. You actually don't want there to be that much deviance from an ideal fitting model. So if this is the best case over here, you don't want very much deviance from that. So we want that TLI, that Tucker-Lewis index, to be large. Okay, so a couple measures of model fit: root mean square residual, Tucker-Lewis index, and there are a bunch more that can be discussed under the structural equation modeling framework. What you're going to see if you get into structural equation modeling is you're going to see that they often give cutoff values. Okay, they give cutoff values. And these cutoff values here are not, they shouldn't be taken with too much seriousness, right? So you look at the RMSEA and say smaller than this is indicating a good fit. If it gets a little bit larger, then it's fair. If it gets very larger, 0.10 is a poor fit. again, you want to compare that to the stuff you're studying. It's almost like trying to compare R-squared values. Don't get too hung up on these particular ranges that you're looking at here. Okay, and that's important because sometimes people do make such a big deal about those numbers. They say, oh, it's a bad fit, it's a good fit. But again, you're comparing it to the literature. Always compare it to the literature so you can assess your model fit relative to what's been found before. Okay, now let's talk about the CFA model. And this is the confirmatory factor analysis model. So instead of EFA, it's now CFA. And when we talk about the confirmatory factor analysis model, we have to see what's different about it. Okay, so start off with our knowledge of EFA. Okay, start off with our knowledge of EFA, and then let's see what's different from CFA. Maybe there's not much different, right? Well, let's kind of see how different can it really be. And that's a good place to start with EFA and say, well, what else could be out there? And let's have a look. So let's see. Looks the same, right? Looks the same. We have a random vector y of scores on the m variables. This is a direct mirror of exploratory factor analysis. And we have p factors. So we have our loading matrix that contains the loadings. Sorry, it's a little bit blurry. There's our eta. Well, that's just a vector. It's a latent variable vector. That looks a lot like the F, right? So far, this is looking pretty darn similar. Because you got a loading, you got these hypothetical variables, which are F, and then you have the errors associated with the latent variables. So when you look at this, you say, my goodness, this looks exactly, right? This looks exactly like the EFA model. Yet it's given a new name because this here, other than notation, right? Other than notation, is this not the same thing as this? This is what we developed in the previous class. It's the same thing. So there's got to be something different about it. Otherwise, they won't give it a new name. We have to see what's different about it. How is CFA different from EFA? Now, the implied covariance matrix is expressed through the same fundamental equation as in factor analysis. If you look at equation 2.4, this is the equation we've been talking about forever. They put the loadings on each side of the matrices here, but this is the same idea as in the EFA. Can you reproduce this covariance matrix, or in the case of using correlation matrix? They use different symbols a little bit, but it's the same idea. Okay, it's the same idea, and they talk about the change in notation here. And this is sometimes it's decided by the different packages that are used. And if you Google Lavande package, if ever you do these types of structural equation models and things like that, you'll see a whole host of, I think the package is actually, the documentation on the package, I think, is even bigger than this entire book. So you have to get used to the notations that are being used. So what could possibly be different between the EFA and the CFA? Well, here's the heart of it right here. EFA and CFA are mathematically very similar, since we have the same fundamental equation in both cases. So we were right. We kind of looked at that equation and said, that looks kind of similar. We were exactly right, and Mayer is even telling us that we're right. It's got the same fundamental equation. Okay, so let's see what else could be different. Well, in EFA, we assumed uncorrelated factors by setting the correlation between factors to the identity matrix. So the only thing that could be happening here is this. That was the orthogonal model that we developed in Stevens. So this matrix here had ones along the main diagonal, it had zeros here. In other words, the factors are not able to correlate. Okay, that's the orthogonal model, right? That's the orthogonal model. Well, what would we want to do? Remember we said IQ and we said self-esteem? If you were to do an exploratory factor analysis and you concluded there's this factor and this factor, the game is over. The story is over. You say, well, I think IQ is related to SE. Well, you've done exploratory factor analysis in SPSS. You're done. It's an orthogonal model. So the first case where CFA is different is that you may not want to include such a restriction, since we typically allow for correlated factors. Now, we can talk about this sentence. There's so much going on in that sentence, but here's the idea. Related to what we previously studied, if you're doing a CFA, you could still choose to model that path as 0. You could still do that. You can say, you know what? I just don't want to model it. I'm going to set it to 0. What freedom, right? You want freedom in a statistical procedure? Confirmatory factor analysis and structural equation modeling are so free because you're allowed to say IQ and self-esteem. Nope, I don't. I was going to do a sad face, but that didn't work out. Let's see. You can say, I'm going to set the correlation equal to 0. In CFA, you can do that. In EFA, unless you do a bit more programming, you can't do that. So the CAN version in SPSS is not allowing you to do that. In CFA, you have freedom. So the first thing to realize here is in CFA equals freedom. You have freedom to decide which paths you want to model and which paths you don't. This is what this line is actually generalizing to. Mayer is talking about this particular case of correlating factors, but the more general idea is that you have more control over your model, and therefore some would argue that it's a little bit better for hypothesizing because you get to determine basically everything you want to estimate. Exploratory factor analysis is like a canned routine. It comes preset with some conditions. You don't have control over them. So if you say, I'm going to do an orthogonal factor model, it's setting that correlation equal to 0. You didn't choose that. It's setting it equal to 0. You choose it if you chose the orthogonal model. By choosing the orthogonal model, that's fixed. It's set to 0. In CFA, you have freedom to change those paths, to allow them to be estimated. So you can remove this restriction in the CFA model and allow that path to be modeled. Okay? Give you an example. It's kind of like the difference between CFA and EFA. It's kind of like a manual transmission versus an automatic transmission in a car. Which one is the automatic transmission? This one. You're increasing the speed in your car and it shifts gears when it's ready to shift gears, right? When it decides to shift gears. In other words, it's a canned routine. The CFA, manual transmission. Okay, they hardly make them anymore. But the stick shift, you get to adjust the gears as you want. Okay, I kind of like the CFA model in that regard because I get to decide if I want to change gears at 40 miles per hour or 60. Sometimes I want to rev the engine a little bit more. Sometimes I don't want it to shift gears. This gives you more freedom over all the components of modeling. That's why it's a little bit more applicable to hypothesis testing, because in this instance here, at least, you get to decide whether you model it. But that's not the only instance you get to decide. You can decide in different instances other paths as well, but this is one good example. So by hypothesizing which indicators load on which factors, we put restrictions on the loading matrix. Restrictions sounds like, boy, that doesn't sound very free, but it is free. It is freedom because you are allowed to start with a whole bunch of possibilities and then place restrictions. Okay. So let's make sure that's clear, is that this idea of restrictions, that kind of sounds more like that automatic transmission on the EFA. But what CFA does is it kind of frees everything up, and then you decide where the restrictions should be. That's almost like if I get the manual transmission here, and then I decide from 4th to 5th gear, I want it to be automated. but every other gear, I want to change gears when I'm ready. That would kind of be like placing a restriction. You start off with complete freedom, and then you place some restrictions, right? You tell your son or your daughter, you can go out on Saturday night, but be home by 1. Freedom, restriction. The EFA model, it's kind of got a lot more other restrictions in there that you may not even be aware of. You see the distinction between the two. CFA, a little bit more prone to hypothesis testing, a direct hypothesis. EFA, a little bit more useful for exploratory ventures. That's why it's called exploratory factor analysis versus confirmatory. Exploratory, things are already determined for you a little bit, and you're just going to run the routine. We'll talk about that distinction a little bit more. So the elements related to indicators that do not load on the particular factor are set to 0, and that's an example of setting it to 0 right here. And we'll talk about this more. There's different estimation methods. There's a whole bunch of different estimation methods, but the maximum likelihood is the default. It is a very popular method. It's used in a whole bunch of procedures. But again, there's a whole literature on different estimation procedures, and Mayer will talk about a few others, but we'll just go by maximum likelihood for the most part. Let's take a look here at how this is diagrammed. And this is an example of a confirmatory factor analysis. So this is a CFA. So let's look. Well, we have one factor. We have another factor here. Intrinsic versus extrinsic motivation. That's what they chose to name this factor. Again, remember, there's no evidence that extrinsic and intrinsic motivation exists. Not in this model. They decided to name it that, right? So beware of that. If somebody says, I found a factor for IQ, they found nothing for IQ. They named it IQ. It's not like the archaeological dig. Can't even stress how important that is. This is decided by what we want to call it, based on what we think loads on it. And we kind of say, well, let's call this extrinsic motivation. It looks like extrinsic motivation, but never in the history of factor analysis has somebody found a factor. It just doesn't work that way. Okay. So we have one factor here. We have one factor here. These are the observed variables. Loadings. Notice that the arrows continue to point towards the observed. It's not the other way around, right? It's not this variable pointing to the factor. So we're saying that this factor is giving rise to these variables type of thing. That's so the theory goes. And the what's that one? Intrinsic is giving rise to these. So basically you're saying this factor has these variables as possibilities for loadings, and this factor has these variables for possibilities. Now, how does that differ from EFA? If I were to run an EFA on this, well, maybe I would include all of these observed variables, right? I include all of these. Then what would come out as my factor solution? Well, maybe I would get F1, F2, and I'd have EXT1 to EXT12 load on factor 1. And then maybe I'd have the others here, INT1 to INT5 load on factor 2. And then I might be able to draw the conclusion, looks like factor 1 is made up of these variables, and I'm going to call it EXTR. Maybe factor 2 is made up of these variables, and I'm going to call it intrinsic, INTR. In the confirmatory model, you're not allowing for that exploration. You know, and this may not even show up in the exploratory model. I mean, that would be a perfect solution if it actually, if these are all 0 loadings and these are all like 0 loadings here, and you had the perfect factor structure that duplicated this, that would be a miracle. It's not going to work out that way. But notice in the confirmatory factor analysis, it's almost like a little bit more of an arrogant model, right? How do you know that this variable doesn't load onto here? You don't. You've set it up that way, right? You don't know if it doesn't load onto here. If you weren't sure and you wanted to just explore the data, then do the EFA. But this is a specific hypothesis that you're testing. So that's like, setting these paths and saying, what, I'm not interested in getting at these. I'm only going to specify these in the EFA model. So in this sense, if we were on the deserted island and all we had was the EFA program, it was an R and we had some code, we could set that model up to do this. Okay, this is, one important thing to understand is that the EFA, pending adjustments, if we were to adjust that EFA, we could get to something like this. So when you're looking at CFA and EFA, you're not looking at CFA as like a completely different thing. It just allows more freedom on how you specify the model. And that's why we say EFA is more prone to hypothesis testing, because you're going to take this structure and you want to see how well does this structure fit. You've got a prescribed structure. This is your factor solution, and you want to test this specifically. In a sense, it's almost, well, it's not quite the same, but you can look at the analogy. When we do the ANOVA, there's our Y and there's our X with 3 levels right here. This is a structure that you're imposing on your data, and you want to see how well that fits. Kind of a similar idea. So when you think of ANOVA, we often say, well, ANOVA is kind of like a confirmatory idea because of that. Right? So we say it's supervised, or if you look at the associated discriminant analysis right here, like that, that's supervised. Whereas things like exploratory factor analysis, and as we'll see, cluster analysis towards the end of today and into next week, cluster analysis is unsupervised because you don't have any kind of ideas, apparently, of where the clusters are. That's why that unsupervised idea, if you don't have a prescribed grouping structure, then you're just searching for groups in here. And that's similar to the EFA idea. Okay, so about this, what is the factor analysis going to do? Well, you may notice right here that this particular path, it's going to estimate all these paths. It's going to estimate these. These could be raw coefficients, they can be standardized, and it's going to estimate these, but you may realize something kind of peculiar here is this particular path has a coefficient of 1 that's got a dotted line. This here was set at 1. It was set at 1. It was fixed. It was fixed at 1. Now, why would you want to fix a coefficient at 1? So before you even run the procedure, you're deciding that that's going to be fixed at 1. In other words, you're asking the algorithm to not estimate it. Well, the reason for setting it at 1, there's a couple reasons for it. One is that it could help you with your degrees of freedom. So remember, for a model, when we test a model, we have to have degrees of freedom. Sometimes, in order to have sufficient degrees of freedom, you've got to fix some paths. You've got to fix something in your model. Otherwise, if you try to estimate everything under the sun, well, then you're not going to have any degrees of freedom. And we want to have some degrees of freedom for our model. So you want to have degrees of freedom that are, positive. You want it to be greater than 0. So sometimes that means fixing a path or 2. Also, it gives the latent variable a scale, okay? Because this latent variable, it's latent, like it doesn't exist. So it gives it a scale on which to exist. So it's customary in factor analysis when you're doing confirmatory factor analysis models to just fix one of those paths over here before you assess the model fit. So the same thing is done over here. Then you can run your model and see how well it fits the data. This is a variance associated with this factor that can be estimated. It could also be fixed if you really wanted to, but in this case, they estimated. Here's a covariance between factors. And these are error variances associated with those observed variables. And those can be estimated as well. Sometimes you could actually fix those as well too. So there's a lot of freedom in this. Big picture. What is this going to do? Well, I've put the equations right here. There's my covariance matrix. There's my covariance matrix that's implied based on the parameters that are being estimated. Okay. So remember I said I set us up for this by talking about it earlier. I said, you know, in that factor analysis, we've got like a correlation matrix. And then what did we get? We got the p hat. That was just on the previous page. And you want to see how well this fit is. Well, this is the same idea as what we're doing here. We needed to discuss this in more detail so we can understand how these models are fit, because these models are going to do the same thing. They're going to take a covariance matrix and they're going to say, okay, reproduce it, right? This is, again, structurally, this is what it's doing. There's the covariance matrix between observed variables. Reproduce it. How are you going to reproduce it? So your task as a modeler is to reproduce this. How are you going to reproduce it? You're going to develop a theory. What's your theory? There's your theory. There's the theory. The parameter vector. So by the estimation of this parameter vector, all these parameters and the specification of your model, the way you set up your model, because in this particular case, you're choosing how to set it up. You're saying, I want these to load on here, and I want these to load on here. You're estimating that parameter vector. So you can think of that as representing your theory. Now, I put the equation here as the observed covariance matrix is equal to the covariance matrix implied by the parameter vector, and this is our HO. Our alternative hypothesis is that they're not equal to one another. Now, we got to be very careful here, because when you look at this, which hypothesis would you like to be supported? Which one? Would you like these to be unequal? Or would you like to demonstrate equality? You would like to demonstrate equality. This one wins out. So if you guess this one, you're absolutely right. This one wins out right here, because you have a covariance matrix, and what you're trying to do is get the parameter vector. That's this thing right here. You're trying to get the parameter vector that's going to do the best job at reproducing this. So this equality is actually what you want to see. Okay, it's actually what you want to see, and this is the null hypothesis in structural equation modeling. It's the null hypothesis in structural equation modeling. So let's think of this. If it's the HO that you're wanting to support, right? If it's the HO that you're wanting to support, and we're going to run a chi-square test, a model fit, what do you want your p-value to be? You do not want a small p-value. There's the small one that's going down here. You want the p-value to be not statistically significant. Okay? You want the p-value to be not statistically significant, because a statistically significant p-value, so a small one, like say 0.03, would suggest that these two are different from one another. Right? Remember that when we look at the chi-square test in terms of, you know, just the chi-square like independence test right here. You know, you have a column variable and a row variable. And here you have observed counts in here, right? So you have like 5, 15, say 20. And then what do you have down here? You have the expected ones, the expected counts. Right, there's your chi-square. Well, what do you want to show when you do a chi-square test? Do you want the observed to equal the expected? No, you don't, right? You don't want to equal the expected. In other words, you want to reject that assumption. Well, how do we reject that assumption? We say, you know what, they're not equal. Well, for that particular case, we want, say, p is less than 0.05. We want to reject the null hypothesis. So we don't want to just reproduce the expected counts. right? We don't want to just reproduce the expected counts. That's the idea when we did the chi-square test. We're not trying to reproduce. Look, if you reproduce the expected counts, like if the expected counts in this cell were 5, and this is 15, and this is 20, wow, what are you producing? Are you going to reject the null hypothesis? No, because you're going to say, well, there's no association between C and R. Right? There's no association because actually it actually represents what we would expect under the null hypothesis. But if this frequency, or if this frequency was, say, 3, and this one was equal to 25, and this was equal to 30, now you're seeing a discrepancy between the observed versus the expected. And therefore, we'd want to reject the null hypothesis. Well, if you compare this idea of model fit here to what we're talking about up here, you'll see that the hypothesis you want to be supported is this one, because you're trying to duplicate those parameters. You're trying to reproduce the parameters. So by analogy, in the SEM framework here, you're actually trying to reproduce these things. You're trying to match up the parameters. Now these are observed counts, so it's not quite the same, but you get the idea of what it's doing. It's trying to reproduce that correlation or covariance matrix. It's trying to reproduce the elements. So if this is my matrix right here, and I've got all my values in the matrix, the absolute best case for your particular, your model is right here. The model that you come up with is going to be an exact replica of this. That's the best case. If it's an exact replica of this, what's the difference between the observed versus the expected, or the observed versus the implied? Right? What's the difference between the observed and the implied? Well, there's no difference. And that would be bingo. That would be, wow, I was able to do it. I was able to take a covariance matrix and reproduce the covariance matrix based on my theory. That is impressive. And that's exactly what we're doing with the null hypothesis. Now, the chi-square test is going to say it's not statistically significant, and you're going to go, good. I don't want it to be statistically significant, because if it was statistically significant, like 0.03, 0.05, whatever, if it's statistically significant, what is that suggesting? Oh, they're not equal. In other words, your model, nah, you didn't reproduce this. Whatever theory you have going on, by the way you set this up, that's not matching the data. It's not able to reproduce the data. So this right here, a rejection of the null hypothesis, is not good. You do not want the p-value. So when you do these structural equation modeling things, you want the p-value to be high. You want it to be not statistically significant because of this nature of that model fit that we're talking about. Let's take a quick break. We'll come back and we will further develop the structural equation model, and then we will talk about, we'll further develop the confirmatory model a little bit and then see how it's a special case of the structural equation model. So we'll be right back.